Let's talk a little bit about control charts and the math behind them. What do these three charts have in common? So this is my control chart I created for minutes of sleep. This was the first thing I did to see if the minutes of sleep, total minutes of sleep, was normally distributed. And this is our normal distribution, the theoretical normal distribution. So it turns out these three are all connected very closely. If we would take the control chart and turn it on its head, let me shrink that down a little bit, okay. And if we took this, notice that the 500's here and the 200's here, it's the opposite direction of this, so I'm going to swing it over this way. Yeah, about right there. So if you pictured these dots right here just suddenly falling straight down into these bins, you would see that they create this shape right here. So you can even see it. There's 1, 2, 3 points right there. If they dropped straight down, you can see that that count, that there's 3 in this bar. Those 3 would fall in there. That one right there would fall right here. Over here we'd have 2 from this point and this point, and so on. So this is just showing us, reinforcing why the distribution of the variable is going to impact how it shows up on the control chart. And so why do we need this normal distribution? Well, we're assuming that the distribution down here is roughly normal, because that's going to tell us roughly how the points are going to play out. Remember that this is the, I guess I should move it about right there, and this would be 3 standard deviations, and I'm lining up the edges of the 3 standard deviation with this 3 standard deviation, the 2 with this 2 standard deviation, and so on. So we want the points to follow that. Otherwise, the points could be anywhere on the chart, and there's no really rhyme or reason to what's common cause variation, what's just causing the normal back and forth on a chart, and what's actually something going on, maybe some improvement or some decline or something like that. So if we know that under normal situations it's following a normal distribution, the common cause, the just pure randomness of the points from day to day or hour to hour, or however we're measuring them, if they follow a normal distribution, then we can tell how unlikely something might be, and we can start to sense when something unusual might be going on, out of the ordinary. In other words, these special causes for variation. So if your distribution is not at all following a normal distribution, if, for example, it's way skewed out to the right or something, well, then on your control chart, a lot of the points are going to be out here, and it's going to be easy to break these rules of special cause of variation. You're going to constantly be running into situations where you have 8 or more points on the same side of the average, which is going to trigger all these false alarms. And that's the danger, that's the risk of using a distribution that's not normal, is that you are going to run into all these false alarm situations. And what does that mean in real cases? Well, if we're looking at some kind of quality improvement plan, anytime we have a trigger for a special cause for variation, there's going to be some little mini investigation on what's going on. Is this just randomness, or is something happening here? And if you have these alarms all the time, when it's really nothing even there, it's just randomness, that's going to use up a lot of extra resources. So yes, you could use a control chart for distribution that's not normal, but you'd want to come up with a new set of special rules that are based on that type of distribution. So let's take a look at a couple of those rules and where they come from and their connection to the normal distribution. So this is rule number 1 from the NHS guide. If you have a single point outside the control limits, we're going to think that that's unusual. Now, it could be just random variation, but the point here is if it's random variation, that's not going to happen very often. So we kind of think that probably something's going on. If this makes you think of null hypothesis testing, there's a lot of similarity there. Null hypothesis, if we assume it's true and then we get a really low p-value saying, this is a lot of evidence against the null, you can think of these special causes of variation as evidence against common cause variation, evidence against the idea that the system is in control, that nothing special is going on. So why do we consider a single point outside the control limits as special cause variation? The basic reason is just because it would be unusual to see this occurring by chance alone. Not impossible, not at all impossible. And we're going to calculate what does this mean to be unusual. So when we say that we're outside of the control limits, another way of saying that is we're more than 3 standard deviations away from the mean. So remember that this is the mean. This is mu, Greek letter mu, mean. This starts with the mama sound. This is the Greek letter sigma for standard deviation. Again, both start with that same s sound. And so you can see here we're 1 standard deviation below the mean, 2 standard deviation below the mean, 3 standard deviations below the mean. So 1 point outside, more than 3 standard deviations away from the mean or outside of the control limits, it would have to be over here or way up here. So what are the chances that that would happen? Well, again, if we make the assumption that we're dealing with data that's normally distributed, most of the data is going to be around the average, but some will be out here, a little bit less out here. 99.73% of the data will be between here and here. In other words, will be inside the control limits. So if we went outside the control limits, then we would take a little calculator here. We would take 1 minus 0.99, whoops, sorry, 9973. So 99.73% chance that it's inside the control limits. Everything else would be outside the control limits, and that would be 0.0027. If you wanted to put it as a percent, it would be 0.27%, about 1/4% chance. So I'm going to keep it as a decimal there, 0.0027, or 0.27% chance, not 27% chance. Let me make that clear. It's less than 1% chance. So not very likely to happen by randomness alone. So if we do indeed see a point that's outside of the control limits, we say, probably not randomness alone. It's at least enough of a red flag that we want to investigate why was that point so high, or why was that point so low? And you actually go in and take a look at what was going on there in that particular case. Okay, what about another one? What about this second cause of special cause variation? So this is where we have 8 in a row, either above or below the center line. So again, the reason why we call this special cause variation is by randomness alone, that doesn't tend to happen. If a distribution would tell us that a point above the line is just as likely as a point below this line, it's kind of like flipping coins. What's the chance that if you're flipping a coin, you'd get 8 heads in a row or 8 tails in a row? That's not very likely. It's possible, but not very likely, and so it's going to trigger a red flag that we should go in and investigate. So what's the actual chance? Well, let's break it down into two questions. What's the chance of getting 8 in a row above? If we're thinking about flipping a coin, what's the chance of getting 8 heads in a row? Well, the chance of getting 1 head in a row is 0.5, right? And 2 heads in a row would be 0.5 times 0.5, or 1/2 times 1/2. 3 heads in a row would be 0.5 times 0.5 times 0.5. What we're ending up doing here is we're multiplying 1/2 times 1/2 times 1/2. We're doing that 8 times, and that's going to give us 0.0039. Let's just round that up to 0.004. So the chance of 8 in a row above would be 0.004. Chance of 8 in a row below, or of flipping 8 tails in a row with a coin, is exactly the same. It's 1/2 times 1/2 times 1/2, 8 times in a row, which is going to give you about 0.004. So total chance of, well, you could get 8 in a row above or 8 in a row below. If you're going to flip 8, you're going to add those two to get a 0.008, or we could say 0.8% chance. Again, a little bit less than 1%, just like it was here when we looked at rule number 1. Why don't they give exactly the same percent chance? Just because we're dealing with whole numbers. If we said 2 points more than 3 standard deviations away, suddenly we'd be way below 1%. So we're roughly trying to make each rule so that it's a bit below 1% chance of happening just by pure random chance alone. Again, because that tells us that probably something is going on, either an increase or a decrease beyond what our normal control limits would say.